Hey guys, welcome back. We'll talk about the big picture again. All right, so when we talk about a chemical reaction, all right, let's define it. And I can actually come up a little bit on my page. Sorry about that. There we go. It's two things. It's a rearrangement of atoms. Right, the atoms are moving around. Right, and we're redistributing electrons. Right. Because remember, chemical reactions are the making and breaking of bonds. Right? And for rearranging atoms. Sometimes bonds are made and then broken. Sometimes bonds are broken and then made. Right? And that can happen in 1 and 2 steps. All right? So the question is why? Why does this happen? Right? Why does this happen? So that leads us to the control of a chemical reaction. This is the why does it occur, right? That's the question. The control. All right? And there's 2 controls that we've talked about so far this semester. There's the kinetics. We talked about kinetics. Right? The kinetic control. Primarily, right? What governs kinetics? Will this reaction happen or not? Right? Kinetically speaking. What's the barrier? What's the reaction barrier? Or what's the energy barrier? And that's EA. Right? Activation energy. Right? Depends on how EA is. Okay? And out of kinetics, 2 things arise. Right? What do we get? We get the rate, right? Which is the speed of the reaction. Right? Which rate equals K times concentration at A to the power, right? We also get the mechanism, which is, right, the steps, the sequence of elementary steps. Right? What happens first, second, third, and so on. So that's what kinetics gives us, right? EA. All right. Then there's also thermodynamic control. All right. There's thermodynamic control. All right. And that primarily comes from what? Second law of thermodynamics, right? Delta S universe is positive, right? And from thermodynamic control, 2 things pop out as well, right? It gives us, is the reaction spontaneous? And then also, how far does the reaction proceed? So spontaneous that gives us what? Delta G, right? We're using delta G for the system to be negative. And how far is our equilibrium constant K, right? Right? Tells us how far. Is K bigger than 1, smaller than 1, right? Is K a big number, small number? Okay. So now let's talk about this thermodynamic control a little bit more. All right. Now we're going to say delta G of the system is negative. All right. What makes delta G negative? Right? We can actually have delta S. Well, that's a horrible delta. Let's try that again. Close enough. Delta S of the system can be positive, right? Which means the system is more ordered. It's entropy driven. Right? And then there is less order. I think I said that wrong. Less order in the system, right? It's more disorder. More random or disorder. We can also have delta H of the system be negative, right? Enthalpy driven. Makes sense. It's an exothermic reaction. Which means energy is out of the reaction. All right. So the question then arises, what makes delta H negative? What's going to make our delta H negative? Well, right, what is delta H, first of all? Delta H is heat transfer. At constant pressure. Well, let's write the whole word out. All right, so as this reaction is going, and if energy is coming out, why is it coming out? Well, it's usually a more stable arrangement of what? Well, usually the answer, more stable arrangement of electrons. All right, so electrons are moving, right? That's what's moving. All right, we're moving bonds, we're moving electrons. Okay, so when we talk about the redistribution of electrons, there's technically two ways to do it. There's acid base reactions. Which are basically proton or H plus transfer. And so, especially in general chemistry, we don't look at it from electrons moving, we look at it from the protons moving. And so there is no change in oxidation state. Right? So our oxidation states don't move. Right? So if it's +2, it's +2, and it's always +2. If it's -1, it's -1, right? It doesn't matter. The oxidation states do not change. Obviously, the last one that we're going to get into is redox reactions. And the redox reactions are, of course, electron transfer reactions, right? And there is an obvious change in oxidation state. All right, so that's what we have going on there, all right? And so that's the big picture, why this is happening, right? Why are all these happening? I'm going to zoom out. All right, and we talk about, well, I can't zoom out any more than that. And so back to this, chemical reactions, right? We're taking A, B plus C, D, and we're switching them, right? Right, we're switching. Why are we switching? Why is that happening? Well, we're making and breaking bonds, and we're redistributing the electrons, right? Okay, now there's some energy required to get that going, and the actual steps of it, the overall energy change of it, right? And we know how far that reaction can proceed under the conditions. Most of the time, right, one of these two is going to be positive or negative. But if we're talking about delta H and electrons, right, most of the time we're talking about exothermic reactions. And a lot of times these redox reactions, right, most of them, your combustion reaction is a redox reaction, right? So when even hydrogen, propane's burning, it's still energy coming out, right? And we're changing, oxygen gas is going from 0 to -2, okay? And so that happens a lot. Right, oxygen, it's a violent reaction. A lot of heat comes out, and we use it for cooking and heating, and even fuel for like forklifts and such. And so this redistribution of electrons is very important, and that's what we're going to get to coming up. Is can we predict the redistribution of electrons? Can we predict that? Can we predict how it's going to go? And then can we control it in a way we can get useful work out of it? So that's where we're going. If you have any questions, reach out. Otherwise, we'll see you next time. Take care.